Okay, let me know if you have any questions. I might go over a couple things, but I'm not feeling super well. So I may cut the live stream short. I am not sure who will be here and who won't be here. I don't think that the quiz is going to be that bad. I think the formative has been challenging enough that if you know that, you should be okay. And you have your notes. You have your 2 notes. Your note for the heating curve, cooling curve stuff. You have your dissolution notes. You have your PVNRT, your assumption notes. You should be okay. I actually think the formative I gave out was harder. I know I need to post up answers. Oh, I need to do that. Post answers. Or Gupta's formative. I'll get that in. I just totally forgot. My bad. Okay, let me know if you have any questions, and if you don't, yeah. But I also realized that Mrs. Gupta went over all the content probably in her live stream at 4 to 6 as well. So it might, yeah. Ugh, my voice is like dying. So let me know if you have any questions, and then if you don't, I can go over some practice problems and stuff, but I can also go over some content related things. Oh, never mind, I have people. Still at school. Oh, this has stuff on it. These physics kids. Can you link Janan Gupta's live stream, please? She just finished, I think. She finished from 4 to 5. I think it's on school, it's on Facebook group. That's where she usually posts her live stream. If you don't have a Facebook group, I can give you a link. Sure. Yeah, hold on. I don't think we meant it for it to collide, but it did. Yeah. Okay. If no one has anything, I can cover concepts, I guess. Or I can go over the practice test. What would you like me to do? I think even though people don't feel super strong about this stuff, I don't think it's that bad. That's what I personally think. Okay, let me go over the heating and cooling curves and things like that so that I can just hit all the stuff I need to hit. So 2.1, 2.2. So this is with the phase change curves. Let me see if I have enough space. Okay, so these are the phase change curves. You can really see these curves in 2 different styles. I'm going to show you the main one first, the one that is the most common kind that you see. And that's the one with temperature on this side. I don't want to go on this side. This is time. And it goes like D, 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 D. Okay. Every time there is a slant or a diagonal, all of these, I should have just drawn it in this color. All of these are basically where it's in a phase, like so a solid phase, a liquid phase, and a gas phase. Okay. As is indicated by the rise of temperature, kinetic energy is increasing. So in the red, KE is increasing. because temperature is changing. You are not changing the states of the matter. So the states of the phases don't change. Do not change. Okay. The temperature affects the kinetic energy because, well, there's the equation that tells them its relation, but also the fact that, sure, I can go over this and then let me go over the practice tests. So the temperature is also increasing because when the molecules are able to move faster, that is going to increase the kinetic energy because kinetic energy has something to do with the movement of things, of the molecules. In here, the flat lines represent this is going from solid to liquid. Oops, I drew this wrong. I drew this without thinking, that's why. So this is going to be super long compared to this one, right? And does anyone remember why this is longer than this one? Okay. The blue ones represent potential energy changes, okay, and no kinetic energy change. For here, potential energy doesn't change because if potential energy is changing, that means bonds are breaking, and that means phases are changing. So when PE changes, the phases are shifting. Okay, so changing phases. All the energy that you take in from the continuous heating or whatever you're doing is basically being absorbed into the molecule to be used in the bonds, and the bonds are breaking. So the potential energy is being broken, and so the potential energy is changing, but then kinetic energy is not. Okay, and this one is shorter than this one because the liquid and gas phase, they're just farther apart in terms of distances. And in ideal gas, we say that the IMF is negligible. So that means that in order to get almost to a zero, they have to be super far apart compared to solid and liquid. And it's important to know how to draw particulate level diagrams for all of these phases. And I have a link that I don't know if I saved. But I have a link for this stuff, but I can also show it to you. So for solid, it must be in uniform places. So for solid, it could be like 1, 2, 3, 4, but they're like in a cube, right? And then for actually I should do 6. And then for liquid, solid to liquid, there's going to be some amount of solid, and then there's like a little bit of liquid, and they could be a little more disorderly. So you could like label it that way. Liquid here, 6, and making sure you do 6. And then liquid to gas, so I have 1, maybe 4, and then like 2. That's the gases, and like 1, 2, 3, 4, 5, 6, something like that. So that could be my particulate level diagrams. Oh, I don't know if you can see these. Oops. And you would have to label them during the exam. Yeah. For this, do we only need to understand the concepts, or do we need to know how to do problems from it? If you're talking about like heat of enthalpy and vaporization, we haven't hit that yet. So you do have to know how to do conceptual problems. It's hard for us to ask any numerical problems from this because we haven't been given anything. The only numerical things you have to know for this test are the gas over water and the PV and RT. I think those are the main ones. And molarity. Yeah. So calculations, you only have 3. Okay. Any questions on phase changes? And then I need to look at the packet. Okay. Any others? And this is kind of related to Vega's question. So Vega's question is with regards to yellow packet number 3. Vega, B is not true because, so the answer in the packet is wrong. Like I said in class, it's D. And the reason is because when you have a water vapor, that's going to cause a lot more severe burns since it is the energy that it has is bigger. So yeah, than a liquid water at 100 degrees Celsius. So I think that one is just misunderstanding. Okay, if there is no question on this stuff, I am going to show you the other kind. So there's 2 curves. This is the usual curve that you see, but there's another type. It's called a cooling curve. It's actually about the same thing, but it looks like this. It can look like that. There could be like a little blimp. I don't actually know why there's this blimp, and then it goes down. And this could be like from liquid to solid, and this is a cooling curve. Same stuff, temp and time. So it's just cooling and downwards, and the phase changes are right here. Okay, PVNRT. PVNRT, I think the only thing I want to clarify, so we're going to move on, I'm going to do the next unit portions, which is 2.4, 2.5, 2.6. So 2.4 to 2.6. And this is with regards to PVNRT. So PVNRT is an ideal gas equation. Remember that it's ideal. Okay. And remember that R is a constant. T is always expressed in Kelvin. V is the volume of the container because of the postulate that the ideal gas law states. When the gas fills up the volume of its container. That's why. And then P is the pressure of the gas. And this is moles of gas. Remember that this only works for gas particles, and at STP, gas particles equal 22.4 liters per mole for gas. Yeah, I would practice a lot of stoichiometry using this idea. I think that's the best you have and the best practice that you're going to need. So this is partially using stoichiometry, learning how to do things like mass percent, learning how to, figure out like converting from here. And then when you have an equation that's given, like after you get the gas going to solid. So there's a couple different approaches that you should know. So there's this, and then you should know from here, mass percent yield, which I'll go over. And then number 3 is like going to using mole ratio with liquid, mole ratio with an equation. Yeah. So mass percent is always done by looking at, so you're probably going to get a gas. Oh, you can also do mole fraction, although that one is kind of phased out. I did see it in the packet, so I just wanted to mention it too. So I think these are the main ones that you can have. You can have other things like for mole ratio within the equation, you can also get like grams and other things. So for mass percent, you would find basically the grams of the thing that they're interested in, and then divide that usually by the initial gram that is given. So if they're like, oh, this is like, 0.5 gram of this compound, and they're like, oh, they get this gas. Then after you find the moles of that gas, find the grams of that gas using stoichiometry, and then put that over the initial grams. percent yield is the experimental over the theoretical. We're usually going to have to give you the experimental of some sort, and then you divide it by the theoretical and you times it by 100. And then the mole ratio, this one is just strictly stoichiometry. You find the mole of this and then find how much of the mole ratio is within an equation. And then mole fraction is this mole over the total amount of moles. Those are usually the equation types that you see in this process. Okay. And then the last ones we have is molarity, and then the, what is it? The last one we have is molarity stuff for 2.8 and 2.9. Molarity, like I said, all you have to do is remember it's moles of the stuff you're interested in over liters of solution. Okay. For dissolution, it's important to know when it would be positive, would be exothermic reaction, and when it would be endo. So remember that exothermic releases energy. Yes, it releases energy, and endothermic is the one that takes in energy. And you should know which one is cold and which one is hot. You should know which one is negative and which one is positive. So anyone want to contribute that and let me know, and then I can confirm your answer. And when you do dissolution, remember that you must draw particulate level diagrams. The one thing that I'm going to warn you for particulate level diagrams, which I already did in class, is when you draw particulate level diagrams, say for like CaSO4, okay, the Ca, so if I'm drawing a particulate level diagram for CaSO4, I have Ca that's positive. Ca, can you see? Okay, Ca, maybe Ca over here. Oh wait, no. And then Ca over here, Ca over here. And then you're going to draw your SO4 stuff too. Sorry. Exothermic would be hot to touch. Yes, and endothermic would be cold to touch and positive. Yep, that's right, Kathy. Good job. And you should know why that occurs, because the first parts don't really matter. Step one is when the solute divides, right? Or it separates, and then solvent is the second step when the solvent separates. But it's the third step that makes a difference as to whether it's going to be an exothermic or an endothermic reaction. If they like each other, then it's an exothermic reaction, so it releases energy, negative, and it's hot to touch. And if it's that they don't really like each other all that much, then it's an endothermic reaction, the solvent and the solute interaction, and that would cause a positive energy because you're basically, and so it'd be cold to touch. Did I say hot to touch? Oh no. So this is hot to, this is the one that is cold to touch. This is the one that's hot. Because exo, you pour in the heat into the system, and then this one you are drawing the heat from the system inside. Sorry, I'm like a little sick, so I'm hoping I can talk. Okay. SO4. Oh, when you do SO4, so this is like S and then like 4 O's. S. And you need to know which one is negative and which one is positive. So, and it's easy. You can know which one is negative and positive. The one in the back is always negative. The one in the front is positive. When you draw your particulate level diagrams, when it separates and then it goes into the liquid, and it's usually water, and it's interacting with the liquid, remember that if the S is negative, when it binds to, and these are all the O's, and it binds to water molecules, since this one is negative, it's going to bind to the head portions. And the head portions are going to be closer to the water than the negative part. Okay. I think this is something we haven't really like discussed as much, but that's what these look like. So if this is our Ca2 plus, then the oxygen molecules would be much closer when it's surrounding. Okay. And remember that from this phase to this phase, if I drew 8 here, I had better have 8 in the rest of my particular level diagrams, unless they're disappearing for whatever reason. Okay, don't forget this, like which one is attracted to which. Otherwise, I think the rest is pretty self-explanatory. It's not a hard quiz by any means. Any questions on like problems that you guys have or anything? Yeah, I don't think, I'm not expecting this to be that hard. Yeah, it doesn't cover the lab stuff that we did today. That's for I think next time. And it would be mean because I gave you like I gave you a pre-lab that was kind of long and a post-lab that was kind of hard. So if I give you something else on top of that, that's a lot of assessments on the same thing like 15 times. Sure, we can go over 3A and 3B on the practice quiz. 3A and 3B? Oh, you're talking about the calculation. Right, so there's like 2 number 3s. All right, so the ethene one, right? Sure. Let me be able to read my handwriting and then we're good. Where'd you go? Okay, so this problem is asking for a setup. So you always have to know the equation. So I will give you the equation. The equation is a C2H5OH gives you C2H4, and this is our ethene. And this is plus H2O, and this is our gas. The phases are important here because, well, actually, these are all gases. But if it wasn't, then it would be important because you need to know which ones are the ones that are like evaporating and converting and so forth. Okay, so you have a 0.2 grams of this guy. And it's going to be heated until everything of this is, until all the liquid ones are gone. So you start with, so this is all gas. Let me just actually write this. Gas and gas. And you start from C2H, oh, sorry. C2H5OH liquid to C2H5OH gas. Okay, so you have a liquid amount of C2H5OH, and then you heat it up so it turns all into gas, and then the gas is going to go through this equation to give you a certain amount of like water. I mean C2H4 and then water with it. So it's being collected over water like every other problem. Okay, and then so you're trying to figure out how much of the number of moles of C2H4 gas is collected. Okay. All right. So what you're going to do is the first thing is you know you have water and this, and you want just this amount in pure. So what you're going to do is you're going to subtract. Oh, great. So 35.7. So you know that water. Oh, wait, why am I using so many different colors? So you know that the water vapor is 35.7 at this temperature, 4. Okay, but you need it to be an ATM, probably. So this is of water pressure of H2O. So what I'm going to do is I'm going to divide this by 760 to find my ATM. And I get 0.04697 ATM. Okay, So then I'm going to take the amount of the atmospheric. So because P total equals P H2O plus P of the thing that we're interested in this case is PC2H4. So the P total in this case is 0.822. Is going to be 0.04697 plus PC2H4. So the pressure of C2H4 is equivalent to 0.77503 atm. Okay, and then you're going to basically Pufner this equation. So I am going to do it on the bottom here. Sorry. So PV and RT. So this is going to be 0.77503 times what's 0.08854, and then I'm trying to find N probably, and 0.0821, and then temperature was 305. Okay, so the N that I get is 264 mole. And that's your answer for A, for 3A. Okay, B. B, what we are doing is we are finding the percent yield of C2H4 in the experiment. Okay, the C2H4 in this experiment. All right, so what we're going to do first thing is we're going to find, this is our experimental data, and we need to find out how much of this was in the, how much of this is actually going to be C2H4. Oh wait, no, we have the moles, so this is fine. So this is of C2H4, but then we don't know. So this is our experimental value. So this is our experimental. And we need to find the theoretical. The theoretical, how you find it is you do it with the 0.2, and you do stoichiometry based on that. So I'm just going to flip this to the back, and I'm going to write the equation one more time so that you guys remember. So C2H5 OH gives you C2H4 plus H2O. Okay. And you're going to do 0.2 grams of C2H5O of C2H5OH is going to give you 46 grams. And then it's going to give you 1 mole of it. And then you're doing 1 mole of C2H5OH to 1 mole of C2H4. I actually did it by grams by accident. It doesn't actually make a difference because it's a percentage, but I don't have this number. 0.2 divided by 46. Yeah. And the reason that you get a different number between this one and a different number for this one is because this one, when you collect gas over water, that's not necessarily going to be like, every experimental data has some amount of error based on like XYZ error analysis. And so that's why you are going to get a different number between A and part B. So this is like, ideally, if everything went right, what would the answer have been? right? And so the answer that you should have gotten was 0.004347. But when we looked at the volume and the gases that were collected, we realized that that's not actually what was collected. So what you're going to do is percent yield is experimental over theoretical times 100. So in this case, it's 0.00264 over 0.004347 times 100. And this is going to give you times 100. So it's like 60.71%. Any other questions or questions on this? So you're not using the 0.2 until you get the percent yield. I really think that if you're able to finish the packet comfortably, you should be okay. Should you know Avogadro's hypothesis and be able to prove it? No, you do not have to. Actually, I don't know why the molar mass of volatile liquid is not in this quiz, but it's not. I guess it's because, I think it's because we just covered it, so it wasn't fair. Any other questions? I think this one is, the study tips, Janani, is pretty straightforward. I think it's a very like straightforward exam. I don't think there's even like really hard questions. I think it's what it is. So everything I said on the live stream pretty much covers the ideas. So go through this and make sure that you know the stuff that I covered, and make sure you do problems from the packet that correspond to the problems that I basically mentioned. And if you do that, you should be fine. I would go over, I haven't looked at Gupta's formative assessment, but I'm assuming it's not that different from mine. The formative assessments I think is good. Particulate level diagrams, you must know. I've been drilling it for a reason. Yeah. If you are like, oh yeah, everything we covered right now in the live stream was good, you're probably going to be okay. I think the one thing I worry about for students is calculations for PB and NRT. So just make sure you know your PubNerd and you're going to be okay. I don't know why the quiz is not that bad, but it's very straightforward. I would think the packet, and actually I think I think practice test is a fair, it's pretty fair. I think it's actually a little harder than the quiz, which is kind of different. So I think you're going to be in good shape. I know some students are like really nervous. So yeah, I think I kind of already gave you the problems as to what you should review. Just review the stuff I just talked about and you should be fine. It's not like the test where like something comes directly from it or whatever, but it's just PubNerd. So if you know how to apply PubNerd to your situations, you're going to be fine. And knowing your gas over water, I think those are the calculation ones that are kind of, yeah. And then the other ones are like more particulate level diagrams, but you guys should be able to do particulate levels. Just keep it consistent and make sure that whatever is attracted to like water is actually attracted to water or whatever it is. Yeah, study your notes, the 3 things I talked about, and then you're going to be okay. I really do not think that I think this is the easiest quiz so far. Yep. So that's why. Otherwise like I would have like all these things, but I'm not freaking out about it. I'm expecting maybe very little retakes, maybe 0 retakes. It looks really good. I personally think our formative was harder. So study your formatives, study your yellow packet, study the practice test, and you should be good to go. You can email me about questions, but I don't imagine it to be that difficult. I think conceptually, this unit is kind of wonky. It's a little bit hard for people to grasp and understand. And I've been trying to look for resources to help you clarify it, but it's actually been really hard to find. Once I get them, hopefully before the test, I will be able to let you know. But I can tell you that the conceptual misunderstandings are not going to own you for the quiz at all. So I think you'll be okay. Do you have anything else? Oh man, my voice is dying. If you don't have any other questions, I am probably going to take off. Yeah. It's not that I'm not wanting to give you study tips and problems. It's just that this is as straightforward as an exam as it can get. I don't think we're going to have much issues. Okay. I think that's good. I know it's kind of like, for a concept that's very confusing, the review session is very like low key. I'm keeping it low key because that's all you got to know for your quiz. So I'm going to leave it like that. And then if we have misconceptions to cover, we will cover them. And I think there will be more addressed as we learn about IMFs and other things. So it'll be okay, I think. All right. Bye bye.